Okay, hello everybody. Welcome back to Statistics for Linguists. This is our last set of lectures for the semester. We're going to talk about linear mixed effects models, and I'm going to break these lectures down into a two-part set. And the reason I'm doing that is because I'm not much of an expert on linear mixed effects models, and I'm going to rely heavily on people who are to kind of walk you through this topic. And I feel like this is a relatively complicated topic, but if you've followed along with everything we've done so far, it should make sense. And importantly, these models have become important in quantitative analysis of linguistic data, especially over the past decade or so. So I want to make sure you get this material out there because it's useful as well as being important. Before we get into it too deeply, though, I want to point out that our lectures are going to follow these two tutorials that were posted by this linguist at the University of California at Merced named Bodo Winter. And I think they're an easy read and easily understandable and also applicable as well, which is why I want to get them into your brains, I guess. But before I dig into them too deeply, I will point out that I have no relation to this guy, Bodo Winter, whatsoever. He just happens to be another linguist who knows a lot about statistics, more than me, really, and also happens to have the last name of Winter, which is not Winters. It's not my last name, although my ancestors had that last name. But be that as it may, I just think the guy has a cool name, ha ha ha, and also has put together a couple of good tutorials on this topic. So let's walk through them. If you want to go to his website, you can find the first tutorial here. Like I said, I'm gonna break these lectures down into two parts, each one kind of following the two parts of the tutorial. The first one is more about sort of the conceptual reasons why we use linear mixed effects models, and the second one is more about how to use linear mixed effects models in R. I will say as well before we get into it too that this linear mixed effects models is kind of a mouthful, I guess, to try to say over and over again. A number of people, like here it's abbreviated LME. The function that we use in R for them is LMER. So a lot of people call these Elmer or Elmers, I guess. So you can do that if you want. Yeah, that's got a good, nice Midwestern ring to it, Elmer. But either way, I'm just going to call them linear mixed effects models. But if you hear that term, that's where it's coming from. It's the same thing as this. So the tutorial starts off talking about linear models like we used in regression and ANOVA, where the basic function is something like this. And just to show you this tutorial on Mr. Bodo's website, it's right here. And he's talking about pitch and how it might be affected by a speaker's sex. And I guess I'll also preface this by saying that because he's looking at this relationship between sex and pitch, or F0, more technically speaking, I'm going to try to respect the boundary between, or the distinction between sex and gender here, and just say that sex is this biological or physiological thing, and we'll kind of just rely on that to try to explain how people's pitch might differ sort of systematically. But for that reason, I'm going to use sex as a variable quite a bit in here, so try not to chuckle too much, I guess. Be that as it may, the way this model is written out is kind of in the same format as we use in R. So pitch here is the dependent variable, and the little tilde right after it indicates that this is a predictive model. So pitch here is going to take the place of what we've been calling y or y hat. It's our dependent measure. So we're trying to sort of determine what the value of pitch or F0 is based on these two other variables on the right-hand side of this equation. And this is just saying that pitch depends on these other two variables, right? On the independent variable or explanatory variable side of the equation, we have two different elements. And the first, sex, is going to be called a fixed effect in this sort of paradigm of looking at the statistical world. And the other, epsilon, is going to be called a random effect. So before, when we first started talking about this, I kind of broke this part down into what I was calling signal and noise. And you can still kind of think about it in that fashion if you'd like, where the signal kind of corresponds to fixed effects and the noise kind of corresponds to random effects. But the whole point of creating one of these models is to sort of dig into what look like noise and try to get more signal out of it to come up with a better predictive model, I guess you could say. Okay, so with that in mind, why are we drawing this distinction between fixed and random effects? So the model assumes that the fixed effect has an underlying structure that we can rely on. The random effect, on the other hand, reflects the inherent, intellectually impenetrable variation that permeates everything in complex reality. This looks like something I wrote when I wasn't actually saying these words out loud. But there's always going to be some variation or some randomness in any sort of complex phenomenon that's out there if you try to measure it. So you can't get rid of that completely. So there's always going to be kind of that distinction between what we can see reliably as structure in the phenomenon and that which just seems like random variation. So we can't get rid of that completely. But like I said, we're going to try to dig more deeply into that random variation to see if we can't get more information out of it, as it were. So we'll walk through Bodo's basic example of how a linear model works just to get started, and hopefully this should all kind of look familiar. But he's going to create a, he's going to create a vector for pitch here, just using some random numbers between about 240 and 112. And then he's also going to create a vector of sex labels, so female and male, and then combine the two into a data frame. And here we are almost at the end of the semester, and we're learning a new command about just how to create data frames on the fly. So if you want to create a data frame from these two vectors just by combining them together, you can use the data.frame command, it turns out. And he's going to store that into the my.df data frame name. So we can take a look at this. And there you go. It's a data frame. And then also this way you can hopefully see that the female speakers have relatively higher pitch, above 200, compared to the males. And again, this is just made up data. So, this might be each speaker's average F0 over an utterance or something like that, or it might just be one particular measurement of F0 from these speakers, whatever. These three are supposed to be female, and these three on the bottom are supposed to be male. And then we're going to try to figure out whether, this value depends on this value, right? Probably. Okay, so the way we can determine that or test that is to use this linear regression command, which we've seen before. So we're just going to see if pitch depends on sex, and we're going to create a linear model, LM, out of that. And if we run that command, we get a lot of output, which we have learned painstakingly how to interpret over the course of the past few months. All right, my child's playing piano downstairs. All right. Things are getting exciting here. So one thing I'll point out, some interesting points that are made in the tutorial is Professor Winter refers to the p-values as conditional probabilities, which I think is a good way to think about them. So as he puts it, they are the probability of a certain parameter of the model being true under the condition that the null hypothesis is true. So I might repeat that again, but before I do, I want to say that the null hypothesis in this case is that sex has no effect on pitch, right? So we're looking at whether pitch is dependent on sex. The null hypothesis is that no, it doesn't. And then these p-values are the probability that this parameter is true, this estimate is true, given that null hypothesis that pitch does not depend on sex. So if the null hypothesis were true under that condition, this would be a very small probability that we get an intercept like this, which is significantly different from zero. And then we get a very small probability that this estimate of the slope parameter doesn't matter, or that there's no effect basically of the speaker's sex on the F0 value. So what these estimates mean in this particular case is that this is the intercept of the linear model, and then this is the slope value, just depending on this variable. But let's dig into that a little bit further. So R is spitting out the parameters of the model in a similar fashion to what we saw with logistic regressions. The intercept is kind of a default or average value for F0. And if you think about that lecture we did on linear regressions, remember when I looked at sort of the interaction or the two-way logistic regression at the end of it, like there was sort of a default of like the number of STRA productions the men make in the sort of less formal context. That was kind of the default, and then we built on top of that. In this case, our intercept is the default or average value for F0. And then the slope of the linear equation is labeled as sex male. And so the model is just building off of female F0, which is 226.33, just making sure I got that right. So this is our sort of average female F0, and that's going to be the default simply because female comes before male in the alphabet. That's how R just approaches this. So we start out with this kind of default or average F0 for females, and then this is sort of the average effect of being male on top of that F0, right? So it'll be around 226 for females. It'll be negative 98 or 226 minus 98 for males, right? And that's, again, like that logistic regression model where we just looked at the difference between sort of the default and whatever factor we're adding on top of it. So the average male F0 should be 226 minus 98, which would wind up being something like a 128, right? Okay, that's what those model parameters mean. We've seen them before, and hopefully that still corresponds with everything you've learned about them so far, because it's just saying it in a slightly different way. We can try building a similar model with the F0 data that we collected from the class, our class, way back at the beginning of the semester. So I'll load this in here, and we'll kind of run the same analysis on it and get slightly different parameter values. So we have more data, so it'll take a little while to load up. But in case you recall, we have all these different variables in here, like F0, F1, F2. And the ones we care about are whether or not F0 depends on the speaker's sex. And we'll check out if it does. And lo and behold, we get a very strong effect here of the speaker sex, and the p-value is quite small. The t-value is not small, it's negative 19. But anyways, the parameters look similar. They're a little bit lower in both cases. So our intercept value is 209 before we had 226. So that's kind of our default female F0. And then the speaker sex effect is negative 85. So in this case, you'd start out with an average F0 for females, about 209. And then for males, you just take 85 off of that, and you get a value of like 124 or so, which is pretty close to where we were for this. I think it was 128 up here. So we're in the neighborhood, right, which is to be expected. We're kind of doing the same experiment again, except in reality, not with canned examples. So it's nice to know the data kind of lines up with what we can expect from a real sort of data collection process. So in the tutorial, Bodo constructs another example where he investigates the potential effect of age on pitch. And I think I might have collected your age information at some point. Actually, I probably didn't, because normally people don't like to disclose that so much. But I did ask some of you to give me your height information, and that's a little less sensitive information because it's not something you can always conceal so much. So I have information for height, which we can use to kind of try a similar analysis to see if height affects pitch as opposed to age affecting pitch. And in fact, we have kind of good reason to think that height might affect pitch, but let's see if it does for our data set. So we will run a linear regression analysis where F0 depends on height, and we will get a significant p-value out of that process, but we will get sort of radically different looking parameters in our model, right? So before, our intercept was like 220 something maybe, and now, or it was like 209, right? Did I miss this? Yeah, it's in here somewhere. 209 was our previous intercept value. Now it's 661. Okay, that's different. And then this effect was, the slope was negative 85 before, now it's negative 2.85 basically. So that seems radically different as well. And the reason why that's so different, nothing's changed in the data, but what's changed is our model, the way we look at the data, right? So what's different here is that our explanatory variable is a different sort of creature than sex. It's a gradient measure, height. So before, with a categorical variable like sex, we could make one change from female to male and quantify how much of an effect that would have on F0. And I've been talking around this a bit, but I'll acknowledge here that, you know, people are quite interested in the modern day and age about sort of like the blurred lines between the female and male categories in a variety of different ways in life. So we can acknowledge there can be some like fuzziness in that boundary between the two categories, but the way our data is structured is that there's no fuzziness, right? So we're just, this speaker is female, this speaker is male. And it, you know, that sort of categorical distinction will not always necessarily be based on sex or gender or something like that. You can get categorical variables like that. And when you make a switch, you get that sort of absolute difference between the two. But what we're talking about here with height is a different sort of animal. So it's gradient, right? So it can just vary quantitatively along a variable stretching from like negative infinity to infinity on either side. So in the second model, we're evaluating how much of an effect each unit change in height can have on F0. And this is smaller than it was before because people's heights are just measured in centimeters in our database. For the speaker sex effect, we're just having this one wholesale change between female and male. And that had a fairly large effect of like negative 85 hertz. Here, each centimeter has a smaller effect of negative 2.85. That's just something based on, the structure of the variable that we're using, and then you don't need to read too much into it, basically. One of the funny things is, though, basically what this is saying is that if you extend the math all the way back to the point where height equals 0, then the base F0 would be 661. So we're using like sort of the average female speaker here as our base F0, but why should that be a landmark exactly, right? We could go all the way to 0, which is a nice sort of mathematical landmark that is normally the way we think of a linear relationship. That's the intercept value, right? So our intercept value here is 661 hertz, but that kind of doesn't make any sense, really. And the model is saying we start out at 661 hertz, and then for each centimeter in height that we add on top of that, the average F0 will go down by about negative 2.8. So by the time you get up to, female speaker heights, you'd wind up with an average F0 about 210 or so, right? But the problem with this is nobody is 0 centimeters tall. So this sort of landmark doesn't make sense for this particular set of data. And when I first presented this lecture, my wife was pregnant with our daughter. It's now 3 years later, but the joke I made then is that not even my unborn child is 0 centimeters tall. Now she's 3. And she's definitely not 0 centimeters tall. She's over a meter tall. We haven't been able to measure her for a while, but she's probably a good, meter, 5 centimeters or taller than that. She's a bit tall for her age. I haven't measured her F0 yet either. Maybe I should do that and add that to the database. But until I do, let's just keep moving on with the tutorial. And I'll get back to you about whether she fits into the linear regression well or not. Anyways, we can make the intercept value more meaningful by once again positing it as the sort of average F0 value for the data set. So again, instead of taking that landmark of 0 centimeters height or just, the average female F0 or what have you, let's just average across everybody and say that this is like our default F0 value. So we're going to create a different vector called averaged height. And this is just looking at the deviations in height for any individual data point in the database and the mean height. So the mean is going to sort of be functioning as our landmark. We've seen that before many, many times over, just maybe hadn't thought of it in that fashion, but that's how most of the stats in this class have worked so far. And now when we look at this vector, we're just looking at how much each speaker's height deviates from that mean. So for this person, it's negative 5 centimeters. For this person, it's negative 15. For this person, it's plus 18. And for this person, it's plus 7. So this is like, this person is just 18 centimeters taller than the average person in class. That's what that means. So if we run a linear regression on this new data set, where we're looking at averaged height as these numbers right here, if we're looking at these numbers as our explanatory variable, and we keep the same dependent variable F0, then, well, what happens is that we get the same, maybe I'll do this with height like this to make it easier to see this comparison. But like the p-value is going to be the same in both cases. The standard or the t-value, so on and so forth, these statistics don't really change that much, but what does change is the intercept, right? So before we had 661, now we have 183. The slope is the same in both cases. We're just kind of referencing our framework to be centered around the average height of the class. And the person who would have the average height in the class, this model estimates their F0 to be 183 on average, which is still a little bit funny too, right? So we're kind of breaking the whole class down into one group of females, one group of males, and then we're saying let's create sort of an average person who's kind of like halfway between those two groups, and then their average F0 would be 183. So that might also be sort of unrealistic in a different way, but it's also putting that average value into sort of a more human domain, I guess you could say, because 183 is definitely a realistic sort of F0 to expect from somebody. And their height, whatever it would be, I think I got it on the slide here. So their height would be 167 centimeters. That's also a realistic sort of average height for a human being to have. Whereas 661 hertz is not, and 0 centimeters height is not realistic for a human being either. Yeah, and I've got a note here on the bottom. I talked about how we have been doing this all along, but we've converted in this fashion our raw height scores into measures of deviation from the mean height to create this model, just like when we first started looking at covariance way back when, or standard deviation, or any of those measures, so on and so forth. Okay, what we want to do next, or what I want to do next, is that since we recently looked at multiple regressions, we can also play around with building models that have more than one explanatory factor in them. So we've got two potential factors here, both speaker sex and averaged height. Let's see what happens if we try to create a linear regression model where we're considering both of these kind of independently. And in this case, we see that sex has a factor, or sex has a significant effect on F0. And our default here now is 208. But the averaged height does not. However, if you run this again with the interaction term in it as well, then you get a more complicated model where everything seems to be significant. So speaker sex is significant, height is significant, and then the interaction of those two is significant as well. And then these parameters start looking kind of funny. So now we've got this default of 211, and then if we say, now we're splitting the data set up into females and males again. So this is kind of a female average. And then the male effect is that it's reducing average F0 by 65 hertz. But then we get kind of this opposite effect for height. Before, height was having a negative effect. Now it's having a positive effect. And then, but then on top of that, there's this interaction. So it looks like kind of centimeters of height kind of add more or reduce F0 more if you're male than if you're a female. So there's kind of like a combinatory effect there. That's the interaction. Anyways, the tricky part about this, which is also mentioned in the tutorial, which is why I'm talking about this, is that we have to worry about a meaningful and predictive relationship between our two explanatory variables, sex and height, like that connection, that interaction I showed you speaks to that a little bit. But we have a pretty good reason to believe that there is a connection between sex and height in human beings, right? So we can actually even confirm that by running a model where we try to have one predict the other. So how much does averaged height depend on speaker sex here? And it turns out there's a significant effect again. And these are going to be another pair of variables, slope and intercept, that we'd have in a linear model. What do they mean, though? And basically, which is the question I have down at the bottom here. So again, this is sort of using the female's height as like the default, but it's weird because it's negative 3.56. So you wouldn't ever think of somebody's height being negative, but it's a negative deviation from the mean height. So I think on the previous slide, I said our average height for the whole class is 167 centimeters. And this is basically saying the average female in our class has a height about negative 3.5 centimeters below that. So about 164 centimeters, which if you speak American like me is about 5'5" or a little bit less than that. And then if you are a male, there's only a few males in our database, but you'd add on average about 12 centimeters to that. They put you around 176. And that is more like 5'10" or so, I think. 5'9", 5'10", that sort of thing. Anyways, the point is that these are based on sort of that averaged height transformation, which centered everybody's height variable around 0. And the other part of this is that we have more women in the database than men, so the overall average is kind of skewed a bit in that female direction, which is why our intercept is negative. And then the male effect is fairly large in comparison, but it's the result of small numbers of guys in the sample anyway. So we can't really draw too much from this, but that's what these particular parameters happen to mean in this case. Okay, so the problem I wanted to touch upon though is what Bodo calls colinearity. So there's that connection between those two explanatory factors. The specifics of that connection between speaker height and sex isn't that important, but the fact that there is can be problematic. So there's math that it works behind the scenes in multiple regressions. I just kind of waved my hands and pointed you in the direction of the textbook and said, you can look it up there if you want. But that math behind multiple regressions is designed to sort of resolve this colinearity problem, that there are meaningful correlations between different explanatory variables. So if you put them both in there, it's overkill. You're kind of being a bit redundant by creating that big of a model, sort of. The tutorial also talks about a number of other assumptions behind linear models like these. Linearity is number 1. Colinearity up here is number 2. 3 is homoscedasticity. 4 is normality of residuals. 5 is absence of influential data points. There's a lot of them. And in fact, if you go to that tutorial and read through it, it says the little toy example is let's start. And then when you get to the problems, it says don't stop here. So keep starting, keep finishing what you started. But I am going to kind of stop there and say you can just read this, because you should just realize that these are problems. And the really big problem that he mentions at the end is number 6, which is the problem of independence. So at that point, it's kind of so important. There's many exclamation marks along with it. And then also we proceed directly to tutorial 2. So what does he mean by independence? Because it's so problematic. I'll just read at this point a number of quotes from the tutorial itself, because you can say it better than I can. But first of all, in the linear model analyses that we've done so far, each data point came from a different subject. And at this point, you might stop and realize, oh, whoops, this is not really the case for our data set if you go back to it. So because we had multiple data points from individual subjects, like 15 different vowel measurements from Duchamp and so on and so forth, 15 from everybody for that matter. So actually we violated that assumption. See how easy it is to do something wrong in stats? Maybe you're painfully aware of that already, but sometimes you can do it without being aware of it at all. So that's a problem. This is probably not the first nor last time that you or I will misuse statistics, however, no matter how well-intentioned we might be. But Bodo goes on to say that if you elicit multiple responses from each subject, then those responses that come from the same subject cannot be regarded as independent from each other. When you violate the independence assumption, all hell breaks loose, and there are lots of exclamation marks. Or there should be when you do that in R, but R can't always catch those problems for you. So what we're going to try to do is deal with that before it becomes a problem. So part of the deal here is that the random element of our linear model was supposed to be that, in theory. There was supposed to be no way to predict that variance based on one observation to another. But in the models we've run so far, that assumption is not always completely true, because there might be some consistency in the random effect based on within speaker F0 tendencies. And we talked about that a little bit when we were walking through repeated measures ANOVAs a while back. So we were trying to kind of account for that variance a little bit by sort of collecting that random residual variance by subject. But in linear mixed effects models, we're going to come up with a more sophisticated way to sort of deal with that speaker by speaker or subject by subject variance, or model it in a more sophisticated way. So a few more choice quotes here. Unfortunately, violations of the independence assumption are quite frequent in many branches of science, kind of as you've just seen. If you end up with a data set that has non-independencies in it, basically repeated measures from the same subjects or what have you, then you need to resolve these non-independencies at the analysis stage. So this is sort of like, you can think of it as like post-processing. after you've shot your movie footage, you got to put it all together and somehow fix some of the problems in it. And lucky for us, you can do this to a certain extent with these mixed effects models. So that's what we're going to tackle in part 2. And as the tutorial itself says, it's going to be a whirlwind tour of mixed models. So we're not going to go deep into it, but hopefully get enough into it that you can figure out how to use them for your own purposes. Hopefully, again, for good and never evil. All right, I'm going to stop there and pick up part 2 in just a minute.